Welcome to iLecture Online. Our next challenge is going to be finding the Laplace transform of the sine of omega t. Here we're going to use a different method than we did in the previous video. We're going to remember that we can write the sine of omega t in terms of an exponential form like that. So when we replace the function f of t by the sine of omega t, we're now going to replace what omega t is equal to in its exponential form. So this can now be written as the integral of e to the minus st times the quantity e to the j omega t minus e to the minus j omega t, all divided by 2j times dt. And then you can see we can write this as two separate integrals. The first one is going to be as follows. So we can say that f of s is equal to, first of all, we can factor out a 1 over 2j, and that'll be applicable to all of them, times, the first integral now will be e to the minus st times e to the j omega t dt. That's an integral from 0 to infinity. And then we could put the minus here, integral from 0 to infinity of e to the minus st e to the minus j omega t times dt. And then we'll go ahead and integrate both of those separately. The first one, well, before we continue, let's write it in a more compact form. This can be written as 1 over 2j times the integral from 0 to infinity of e to the minus quantity s minus j omega times t. Again, when you apply the negatives here, negative times a negative gives us a positive here, times dt. And then minus the integral from 0 to infinity of e to the minus quantity s plus j omega times t dt. And notice that when you apply the negative sign, you get back what you started with. So now we can go ahead and integrate those. Let's see what we get. F of s is equal to 1 over 2j times. The first integral will be 1 or minus 1 over s minus j omega times e to the minus quantity s minus j omega times t evaluated from 0 to infinity. Minus times the minus becomes a plus, 1 over s plus j omega. And that would be times e to the minus s plus j omega times t evaluated from 0 to infinity. Wow. All right. So far, so good, I believe. Let's take a quick check here. So we have a minus, that becomes a minus times a minus is plus. Here we have s minus j omega, s plus j omega. I think we're good. So now what happens when we plug in the limits? We plug in an infinity, that goes to 0. We plug in 0, that goes to 1. So that will be 0 minus 1. And the same here, 0 minus 1. So this becomes f of s equals 1 over 2j times minus 1 over s minus j omega times, when we plug in the upper limit, we get e to the negative infinity, which is 0, minus e to the 0, which is 1. So we get 0 minus 1. And then here we get plus 1 over s plus j omega. And the same thing again, times 0 minus 1. Now we have to do some algebra. So simplifying this, we get the following. 1 over 2j times, this will be 1 over s minus j omega, and this will be minus 1 over s plus j omega. So now we have to combine those two fractions, which means we have to find the common denominator. So this can be written as 1 over 2j times. The numerator will get s plus j omega minus s minus j omega, all divided by the common denominator of s plus j omega times s minus j omega. So continue to simplify. This is equal to 1 over 2j times s minus s, that's 0. J omega minus j omega is 2j omega in the numerator, divided by the denominator. Notice this is s plus and s minus. This becomes s squared minus j squared omega squared. All right, we're almost there now. Notice we have a j in the numerator, a j in the denominator, a 2 and a 2. That cancels out. And here, j squared, that's the negative 1. Negative 1 times negative 1 is positive. So this becomes omega divided by s squared plus omega squared. And this here would be the Laplace transform of our original equation, f of t equals the sine of omega t. When we take the Laplace transform in the complex frequency domain, we get omega divided by s squared plus omega squared. And that's how we do that in this different method.